Welcome back. So we'll continue this revision through solved problems. So we have seen stability and of course followed by dissipativity, and that's kind of the analysis side of things. And we looked at applications to robustness. Of course, the most important thing as an application is actually how do we use this in feedback control. If the system doesn't have stability, can we stabilize it? If the system has to be dissipative with respect to something, why should it be? Well, because of disturbance, rejection, or 10 other reasons, robustness and things like that. So can we actually through feedback make it dissipative with respect to a particular supply rate? So these are the two possible things that we can do with the analysis results we learned. In some sense, the what do you call, the techniques are really not that great. It basically essentially says that if we can find a feedback such that all the conditions of the analysis problem is satisfied, then we are done, right? So it's not really saying much, but we have seen some special classes of examples where we can do a methodical way of designing and things like that, and then we will hopefully see a couple of examples that are generic enough that we can imitate that method to large class of systems, right? Large but not really large. I mean, it doesn't cover everything for sure. So anyway, within the scope of feedback control, the easiest or the most viable part type of feedback is basically full state feedback, right? So you can actually assume that you have access to all the states as measurements, and then basically use the values of those states, and then create some magical function out of that, and then feed that as a feedback controller, and then hopefully that will produce your asymptotic stable equilibrium. But in reality, most of the time we do not have access to the entire state. Just a simple example, suppose if you are trying to control the surface of an airplane, wing surface or something like that, it's an infinite dimensional system to start with, and you can only control at a finite number of points. So there's no chance in certain cases basically do the entire state. So you have a choice of basically assume that this system is finite dimensional, and hopefully the infinite dimensional parts are approximate to this finite dimensional, and then hopefully it is fine. Technically we call such things as basically projection of an infinite dimensional system onto finite dimensional, and then we work in the finite dimensional and hope for the best, right? So that's one way of thinking about it. But in general, ideally speaking, we should be able to solve the output feedback problem. Output feedback problem is not the easiest, not even in the linear case. Even more difficult is actually through dynamic feedback. Again, it's an output feedback problem, except in the linear case, and we can extend that linear case to some extent to the nonlinear case, where the development of this dynamic controller was thought about like this. So since I don't have access to the complete state, I'm going to first estimate the state and use that as proxy for the actual state, and then compute the controller that stabilizes as if the estimate is the real one, and then combine these both together, and then that produces a dynamic controller. And in fact, Kalman's filter plus regulator put together gives you the LQG controller. And this the fact that these two things can be separated is called, that has very appropriate name, it's separation principle it's called. And then the idea of separation principle is used in nonlinear systems, where you have some kind of estimator part of it, and then use that as a feedback mechanism and treat it as a full state feedback design problem, and then both of them put together, right? But solving for stability is another aspect of it. In this particular class, the easiest thing that we can do is, if we have a dissipative system, then we have an entire class of dissipative systems and the feedback that will stabilize this overall closed loop system, right? So anyway, this is general problem statements. There are no really great solutions to these, and we will leave it at basically saying that either the dissipativity theory produces the feedback interconnection type of result, or the reverse engineering of the standard Lyapunov function theory, either of them will work, right? And then we'll see some specific examples in this class and the next class to see what is possible. You know, obviously not teaching anything brand new at this point, either showing some very high level ideas or just some examples, right? So I'll take up one example. This is not quite simple in the sense that it's not in x1 equals x2 and things like that. It is generic enough that we can think of it as a theoretical problem, but it is special enough that we can actually solve this particular problem, right? It's not the most generic problem. It has a very specific structure. So what is the structure? We have one system that is x dot equals f of x plus g of x times x hat, right? Whereas x hat is a state, okay, completely decoupled from x, and in this particular case I assume that x dot is just perturbed by u, okay. So such systems we call them as cascade systems, in the sense that there's you know, these are coupled system, but the coupling is in one direction. So basically x hat is influencing x, but not x is not influencing x hat, right? If both are measurable and things like that, especially where the control is, we can allow for some function that is perturbing x hat equation also, but we will look at that in a second in terms of how that is possible. But let's see how to address this. Essentially what the idea of what I'm about to show you is, how do I solve this? You know, we can actually try and guess all kinds of Lyapunov functions and things like that, and then probably not reach anywhere, but I'm going to think of it as a very specific idea. Suppose I know somehow the first equation, first system can be stabilized through x hat. You know, if you view x hat as a input to the first system, then basically the logic is the second system becomes kind of an integral controller, and then we can actually find the feedback controller u for the whole system, right? So that's the logic here, right? So again, so if you have a feedback cascade systems, you know, let's say you have a first set of equations that depends on the second state, and the second set of equations depends only on the third state, and but then the coupling doesn't go the opposite direction, and then eventually you have a control at the end, and then that control can be designed in such a way that the entire system is stabilized, right? So the only assumption that we make is each of these, so x2 stabilizes x1, x3 stabilizes x2, and so on and so forth, right? So let's actually explore this particular problem, you know, and then see how we can resolve this problem of cascade systems, right? So if I have this x dot equals f plus g, both functions of x, and I have x hat here, and x hat dot is equal to u. So what should be u is the question, right? So the hint is given in the problem statement itself. So I'm going to basically use that hint, which is essentially saying, you know, let's call this a v1, okay, plus x hat minus alpha of x transpose p x hat minus alpha of x. Many times I don't really specify the dimensions, assuming that you know how to handle the dimensions. You know, p has to be same as this x hat and things like that. Obviously alpha x has to be same as x hat, and so on and so forth, right? So anyway, what is alpha and what is v1? So we make a big assumption. So the assumption is basically x hat, if it is treated as a control for the first equation, it stabilizes the first equation. So in other words, I am going to assume that this is true. Right? So if I replace x hat with some feedback alpha of x, okay, and if it turns out to satisfy your standard Lyapunov derivative condition to be satisfied, less than 0, then we can try to find u such that the overall system is stabilized. So let's see, with this assumption, basically I'm going to compute the v dot for the overall system. So that becomes v1 prime of x times x dot, of course, which is nothing but f plus g x hat, okay, plus 2 times x hat minus alpha transpose p. This is what we have to be careful, x hat dot minus alpha prime of x times x dot, right. So we'll do this trick, vf plus g alpha here, which we know is strictly negative, plus v prime times g times x hat minus alpha, right. So you can clearly see where I'm going. This x minus alpha becomes common factor between the next one and things like that, right. So transpose p times x hat dot is u minus, for the time being I'm going to leave to this as alpha dot, okay. I'll explain that a little bit later. So since we know that this is strictly less than 0, I can write this as strictly less than for all x non-zero. X hat minus alpha transpose, okay, p times, well, I'll put 2 here anyway, u minus alpha dot minus well, actually plus half p inverse g transpose v transpose, okay. Where did I get this? This is basically coming here with the transpose happening, and then 2 is taken care of by this half, and then p is taken care of by this p inverse, right. So you can clearly see that I can basically pick u to be equal to some minus constant x hat minus alpha, right, plus alpha dot minus half p inverse g transpose v transpose, okay. So so p is coming from our Lyapunov function, which is a choice. V is also something we assume that we know it exists for the first equation. So g is the part of the system parameter. This c can be design parameter, some positive number, and x minus alpha. So basically, so suppose if I pick this u, and we'll discuss about the legitimacy of that. Basically, v dot is going to be less than or equal to this minus v1 prime, sorry, v1 times f plus g alpha, which we know is less than 0 if for all x not equal to 0, minus c times x minus alpha transpose p x minus alpha, right. So that shows that this system is positive definite for the Lyapunov function part, and then strictly negative definite for v dot part, right. So therefore we can show this system is locally asymptotically stable by realizing that this is also a radially unbounded function. We can if v1 happens to be radially unbounded, then we can conclude that this system is globally asymptotically stable, right. So now what about this? Well, everything is fine. X hat is one of the states, alpha x is a function of the first state, p inverse is a design parameter, g transpose of x, v transpose 3, all this is available. But what about alpha dot? Well, we have to assume hopefully that alpha of x is actually differentiable, in which case I am going to get alpha prime times x dot, but alpha prime of x times x dot is nothing but f plus g times x hat. Again, all of these things are available. So the only assumption in all these things from us, this thing is basically this alpha x has to be C1 continuous, and if we cannot find a control law that is differentiable for the first part, then this entire procedure is not going to work, or rather at least the theory that we use does not work that efficiently. We have to be careful, and instead of alpha dot we may have to do something else. Okay, so so you can imagine if we had something like this. Suppose if I had, instead of f plus gx hat x hat dot is equal to u, okay, if I had, I don't know, f x hat plus g hat u, then what can we do? Well, hopefully this g hat is invertible, and you know, we can essentially, whatever we want to equate, we can subtract this f and then multiply this inverse of this, right? That's the only idea that we have at this point. Really, you know, there's not much more to it. So one can handle such things if certain invertibility conditions are satisfied. You know, now suppose if I had something like this. Right. So what do I do? Well, I treat this first problem as if I'm controlling with this as u, and then once I have that, I will get a rewrite this problem in such a way that I'll consider that as first part, and then basically redesign. So this cascade structure, I would urge you to basically try to solve this particular problem. How do I imitate this particular process for even more cascades, right? So that is how it works, and then we will actually look at one more example where this x1 dot is equal to minus x1 power 4 minus x1 cube plus x2, and then x2 dot is equal to u. Okay, so what I have here, x1 dot is equal to minus x1 power 4 minus x1 cube plus x2, and x2 dot is equal to u. Okay, now you know, for the first part, since it's a scalar system, I could actually consider something like x1 is equal to half x1 square and see what happens, right? And then v dot is basically v prime times whatever that, and that's x1 times minus x1 power 4 minus x1 cube plus x2. And that you can clearly see it's going to give me minus x1 power 5 minus x1 power 4 plus x2 x1. Okay, clearly basically this is a negative part, so it's a good thing for us to have, but this is unfortunately sign indefinite. Depending on x1, it can be positive or negative, and that has to be cancelled from this. And you can clearly see if I choose x2 is equal to x1 power 4, that works out for me, right? So in other words, what this is saying is alpha of x1, in the previous example, I can choose it to be x1 power 4. All this particular thing is saying is basically, if I treat this first one as a feedback control problem and I choose x2 equals x power 4, then this whole thing works, right? And you know, I can redo the entire process, but if you recall, u has to be equal to minus c times x2 minus alpha of x1. That's the first part. And let's see, you know, plus alpha dot minus half p inverse g transpose v prime and things like that. Okay, so alpha dot is essentially 4x1 cube times minus x1 power 4 minus x1 cube plus x2, right? And that's the alpha dot part, and the last one is basically minus half p inverse g transpose v prime, where you know, v of x I can pick to be v1 of x, which is half x1 square plus half x 2 minus alpha of x1 whole square, so that p is 1, right? So this is nothing but minus half times g happens to be 1 and v prime is simply x1, right? So that's your feedback control law that will stabilize entire system. So this is a nice procedure whenever we have this cascade systems, and then this can be extended to even more complex systems. Okay.